Hi everyone. Today we're going to finish up our notes on limits, continuity, and differentiability. So we got through about halfway through these notes, so we'll pick this up at the bottom of the second page with example 5. We were evaluating this limit, and we had talked about multiplying by the common denominator of our two complex fractions. Remember, a complex fraction is a fraction within a larger fraction. So get a common denominator, multiply the numerator and denominator of the big fraction by those, right? And so we get the complex fractions to go away, which is great, right? And then we combine like terms, and then we can go ahead and cancel out these x's. So this was where we left off. And so now our next step, after we divide the x's, is just to rewrite what we have, right? So we get -1 over 3 times quantity 3 plus x. And now remember, our goal with the limit question is let's just take the x value we are approaching. Can we just plug it in? And now we finally can, right? And so I no longer need to write limit. And now I can just simplify, and I get -1/9. Okay, so we talked about limits as a way to set up a discussion on continuity, right? So let's take a look. What is the definition of continuity? A function is continuous at x equals c, IFF, right? IFF, the first time I saw this, I thought, wow, my college professor can't spell. Turns out I just didn't know that this was a common shorthand for the phrase if and only if. So a function is continuous at an x value, x equals c, if and only if two things are true, right? The limit, as we approach this function, right, the limit of the function as we approach c from the left and the right are both equal, which means that the limit exists, right? So this is just a fancy way of putting the definition of a limit within the definition of continuity, right? Does the limit as x approaches c exist, right? This must be true, right? So, limit as x approaches c exists. Does it equal some number which is the same as the value of our function at c, right? That would be f of c, okay? And so we can say then, if a function is continuous, you'll notice I use cont as a shorthand for continuous. If a function is continuous at all points in its domain, then it is a continuous function, okay? And so the last thing we're going to put in this box here is just some examples of continuous functions. So things like y equals x squared, y equals x, y equals root x. And now you might be looking at something like root x and going, hey, you can't plug negative numbers into root x, right? Well, remember, the domain of the square root function is bracket 0 to infinity. So within that domain, this is a continuous function, okay? And so then we have things like sine of x and cosine of x. And I just wrote a little reminder here for what these graphs look like. Go back to your trig notes, section 4.1, section 4.2 in trig, right? Go back, review these graphs, right? These are good ones to know. Absolute value of x, horizontal lines like y equals 1, e to the x, and then natural log of x. You might think same issue as root x, right? Natural log, this is a good graph to remember what it looks like, right? So natural log, remember, is the inverse of e to the x, right? Natural log, you can only plug positive numbers into it, right? But again, within its domain, right, meaning if I'm just tracing these points here, right, this is continuous, okay? So, there's a vertical asymptote at the y-axis. Does that matter? No, right? Can't plug in a negative. Does that matter? No. This is a continuous function because none of those things are in the domain of natural log of x, okay? So let's look at some graphs where we have some issues, okay? So A here gives us this rational function, x squared minus 1 over x minus 1. So really, continuity comes down to two things. What is the value of the function, right? Well, if I plug 1 into this function, I get does not exist, okay? And then you could stop right there, right? If the function value doesn't exist, you know it's not continuous, but let's just do the definition, okay? Limit as x approaches 1 of f of x, right? If I trace this graph from the left and the right, I get that the limit is 2, right? And so, right, we have function value doesn't exist, limit is some number, so this is not continuous at x equals 1. Okay, let's look at g of x. G of x gives us this piecewise function, right? And so what does this have? G of 1 is 1, right? We can see this floating dot on the graph. Okay, what is the limit of g of x as x approaches 1? So again, if I trace the graph, I'm tracing towards 2 again, right? So trace from the left. I don't jump down, right? The y coordinates are all getting closer to 2. Same thing from the right. They're all getting closer to 2. This floating dot doesn't matter. And so again, we do not have continuity at x equals 1, right? And then our last example here, h of x, right? So looking at this one, right, this just looks like a line. H of 1 is 2. Limit as x approaches 1 of h of x, also 2. So this is our only function that is continuous at x equals 1. Okay, so again, it comes back to the definition, right? You're going to get asked on our test, on the AP test, justify, right? When you're asked to justify, come back to the definition. Does the limit as x approaches c equal the value of the function? Do they equal the same number? If both of them do not exist, right, that doesn't count. Does not exist, not a number. Same thing with infinity, right? Not a number. Okay, let's keep going. Okay, and so we use our discussion on continuity to talk about derivatives, right? And so first up, we start off with limit definition of the derivative. I put a big old ugly star next to this, right? This is something you should remember from Algebra 1, right? F prime of x is limit as h approaches 0, f of x plus h minus f of x all over h. Some of you in Calc A may have preferred the alternate limit definition of the derivative. I shorten this up to LDD, right? Some people like this one better because there's no h, right? Limit as x approaches a, f of x minus f of a over x minus a. You know, some of you guys don't like the h business in just the standard limit definition, but remember, h you can just think of as like horizontal distance, right? You know, this formula comes from slope of the secant line, just like the alternate limit definition does, right? Everything is just based on slope. All the h is saying is that we're letting the distance between my 2 points get closer and closer to 0. That turns my secant into a tangent, right? All that fun stuff from Calc A last year, okay? Differentiability. A function f of x is differentiable at a point c if it has a derivative at c. So differentiable, think of this as kind of like an adjective, okay? Right? It's a property, right? Differentiability is a property, right? You know, if a function is differentiable at that point or not. A function that is differentiable at every point in its domain is called a differentiable function, okay? So let's talk about differentiability real quick, okay? And we're going to mix this in with continuity. Let's take a look at this graph, and we're going to take a look at this at 3 specific x values, okay? So the first thing I want to start with is an x value where the function is both differentiable and continuous. And that would be something like -4. Now, a lot of students sometimes will make a silly mistake. They'll look at this, so, you know, here real quick, we'll just label. We'll say this is the graph of f of x. Okay, what is f prime of -4? That is a horizontal tangent line right there, but sometimes students will make a silly mistake and say, oh, no, that doesn't exist, right? But actually, it's just 0, right? So this is a point at -4 where the function is both continuous and differentiable. Compare and contrast this to the point at x equals 1, where the function is continuous, but is it differentiable? No. And this is where we have to look back in our Calc A notes, right? And remember that we talked about the idea of a corner, right, as a non-differentiable thing that can happen on your graph, right? Corners, cusps, vertical tangents. And then the last big one is discontinuity. If you look at this graph at x equals -2, right? Negative 2 from the left, we're going all the way down to negative 8, right? Negative 2 from the right, we're going up to positive 2, right? So this is not continuous at negative 2, and therefore not differentiable at negative 2, okay? So really, the two x values that are no good on this graph are negative 2 and positive 1. Every other x value on this graph, the function is both continuous and differentiable. If you just pick a random other x value, if I just pick, I don't know, this point right here, right, it is both continuous and differentiable there. There's no issues, right? If I pick this point right here, right, again, both continuous and differentiable, right? So that's the same thing with negative 4, right? So it's just x equals negative 2 and x equals 1 where this graph has some issues, okay? Last thing I want to mention here before we wrap up, something you probably talked about in Calc A, right, is this idea that differentiability implies continuity. Okay, so, meaning if I tell you, hey, the derivative at x equals negative 4 exists, then by default, you know that the function is continuous at negative 4. Okay, whereas the opposite of this, right, continuity does not imply differentiability, right? Take a look at the graph at x equals 1. If I told you the graph is continuous at x equals 1, you cannot assume that it's differentiable there because, again, corners, cusps, vertical tangents, those are all places where your function is continuous, but there is no derivative. Okay? Okay, and that'll wrap things up for today. I'll see you next time.